All right, we're starting section 8.2 here, the first part of 8.2. We're using confidence intervals now with proportions. So in 8.2, we deal with how to try to estimate the population proportion using our p hat surrounded by a confidence interval. And then in 8.3, we'll do the same thing, but with trying to estimate the population mean. So just like chapter 7, broke things up. The first section of this chapter 8.1 was dealing with confidence intervals in general. And then 8.2 is how we're going to use confidence intervals to estimate a population proportion. And 8.3 will be how to estimate a population mean using confidence intervals as well. All right, so then in this part, we're going to check some conditions before. We're going to kind of get back into a 4-step process. We used 4-step process at the beginning of our book in earlier chapters. Gotten away from it and used kind of a 3-step process. Now we're getting back to our 4-step process, and we will be using that 4-step process really for the rest of our book. All right, so we want to look at 3 different conditions that we're going to have to check. We're going to look at figuring out how to find our critical value, which we need in order to find our margin of error. And we'll use a z-score table as well as our calculators to do that. We'll show you both methods. And then we'll actually construct and interpret the confidence interval. So we talked about confidence intervals again in general last section, but now we're applying them specifically to population proportions. All right, so an activity that we usually do in class is I have a container of beads, different colored beads. And so our goal is going to be to estimate the actual number of red beads. Actually, we do red and dark pink. So there's a light pink, a dark pink, and a red. And so we're looking at red as being red or the dark pink beads. All right, and so if we're doing this in class, I would break you guys up into groups of 3 or 4. And we would take a scoop, have someone come up, take a scoop of beads out of the container, and then that will be our sample. And we will calculate the number of red beads and the number of non-red beads. And we would try to use that to estimate the total number of, or the proportion, true proportion of red beads in the container. So since we're not really in class, we'll kind of work through this a little bit of an example, together, assuming, we had done it. But in class, I would have had you guys break up into groups and try to come up with your best estimate based on the sample data that we collected. All right, so let's assume for a minute that we went ahead and did that sample, and in our little scoop of beads out of the container of beads, we got 12 red beads. And then we got 93 that were not red, that were a different color. And so we want to think about the best estimate or a confidence interval to estimate the number of proportion of red beads in our container. So the first thing we probably want to think about is doing a point estimator. And for us, we know that p hat will be an estimator, an unbiased estimator of the true proportion of red beads in the container. So what would our p hat be in this case? Well, we had 12 red over a total of, what would that be, 105 red beads. All right, so that gives us a p hat of about 11%. So 11% of our sample were red beads. All right, so now what we want to think about is, okay, so how can we use that to estimate the proportion of red beads in our container of beads? All right, so the first thing we want to think about is if the sample size is large enough, then we know that n times p, and n times 1 minus p are both going to be 10. I think we're okay in this case. Of course, we don't really know what p is, right? We don't know the proportion, so that we'll talk about that. Since we don't, the large count condition that allows us to say that the sampling distribution of p hat is normal is based on n times p, the p being the true proportion, and n times 1 minus p. But we don't know the true proportion because remember, we're trying to estimate this. So what are we going to do instead? And so what we will do is we will go ahead and use we will use p hat in place of p. All right. And we have a similar issue with standard deviation, right? So the standard deviation of the sampling distribution is the square root of p times 1 minus p all over n. But again, we don't know what p is, so that's going to be an issue as well. We're trying to estimate p. We can't really very well pretend like we know p, so we don't know p. If we knew what p was and be able to put it into these formulas, then we wouldn't be trying to estimate it by taking a sample. All right, so in practice, we do not know the value of p. Last chapter, we kind of pretended in all of our examples in section 7.2 when we were doing sampling distribution of p hat, we were in every problem, we kind of assumed we knew what p was, but in reality, we're not going to know. So this chapter is going to get a little bit more realistic here. All right, so if our sample size is rather large, then we know the standard deviation of the sampling distribution, or the spread of our sampling distribution of p hat, is going to be fairly narrow. And so our p hat will be pretty close to p, assuming the sample is large and is fairly large. So we are going to go ahead and just replace p with p hat when we're checking for our normal condition. All right, and so some other things that we have to check in order to do our 4-step process, or in order to calculate our confidence interval, we need to make sure 3 things: that the data that we've selected, the simple random sample, is actually a randomized sample, right? So the data comes from designed simple random sample. We'll get to this idea of a randomized experiment more in later chapters, but randomized experiment or a random sample, simple random sample. We have to make sure that our independence isn't violated too badly by checking our 10% condition, checking that our sample size is not bigger than 1/10 of our population. And then the large count conditions. And this is where we see we used to use, last chapter, we used n times p and n times 1 minus p. But again, we don't know the true proportion. So we're assuming that our p hat is not going to be too far off from our p. And so we will use p hat, basically, because we have no other choice. Okay, and then we have a similar problem when we do our standard deviation of the sampling distribution of p hat. That's the square root of p times 1 minus p all over n. That's the standard deviation of the sampling distribution of p hat. We don't know p, so we can't calculate the standard deviation of the sampling distribution of p hat. So instead, we calculate what we call the standard error. And so look, it looks a lot like the formula for the standard deviation of the sampling distribution of p hat, but instead we're using p hats rather than the p. And so to differentiate this from the standard deviation, because it's not going to be exactly the same, right? Your p hat is not always going to be p. Again, they'll be close if the sample size is large enough, but they're not going to be the exact same value. And so to differentiate these two things, we call this one with the p hats in it, we call it the standard error rather than the standard deviation. So it's the standard error of the sampling distribution of p hat. Okay. All right, so when the standard deviation of a statistic is estimated from the actual data, from the sample data, the result is referred to as a standard error of the statistic. So we're going to see this in section 8.3 as well when we deal with the standard deviation of the sampling distribution of X bar. We're also going to have to use a standard error because we won't know sigma in that case. All right. All right, so what we looked at in the last chapter, in the last section in 8.1, was when we do a confidence interval, it's going to be the statistic, sometimes referred to as the point estimate, plus or minus some critical value times the standard deviation of the statistic. Now, we just talked about how that's really not going to be the standard deviation of the statistic. Instead, that's going to be the standard error of the statistic. And so we know that was the general sort of formula that we talked about in the last section, but now we'll apply it more specifically to proportions. So if the large count condition is met, we know that we have a sampling distribution of p hat, which is a normal curve, or at least approximately normal. To find the level C confidence interval, we need to catch sort of the central area C under that normal curve. So a picture is a little bit better here. So you can see if I'm doing a 95% confidence interval, then 95% is going to be inside of the area under that normal curve is going to be between the two values. And then that means 5% is going to be outside that area, split equally between those two shaded regions. So in this case, that means we're going to have about 2.5% in each one of those. Now, back when we were using the empirical rule, a 95% confidence, right? You know, to be 95% mean that we were plus or minus 2 standard deviation. So that would have given us a z-score, a z-value of 2. But in reality, the z table or table A gives us a little bit more accurate result. Like often we're going to look for a 95% confidence interval, right? That's probably most of the time when we do a confidence interval, it'll be a 95%. But we're not going to use a z of 2 like we would get from the empirical rule. Instead, we're going to use the more accurate value, which is 1.96, close to 2. But you know, the empirical rule was kind of back before we really understood z-scores and how to calculate those. So we're going to use a critical z-score value of 1.96 when we have a 95% confidence level. All right, so let's think about using our table A to find the critical value, the critical z-score value. So z star is the symbol that we use for our critical value. So z star is very specific, and it depends on our confidence level. All right. So again, we're assuming the large count condition has been met so that our sampling distribution of p hat will be normal. And so then we want an 80% confidence interval. So that means inside the shaded region in the middle there is 80%. That means we have 20% outside, equally split between the two tails. And so that will be a 10% in each tail. All right, so 10% to the left of that value, that z value, that will be sort of over here, okay, on the left. All right. So if we look at our z-score table, we will be looking for, in the body of the table, not on the margins, but in the body of the table, we're looking for 0.1 or the closest number to 0.1. So if you look sort of over the left bottom corner here, you have some values here that are all cycled. They're all about 0.1. You could see here that it's somewhere between these two values. These are the two values closest to 0.1 on our z-score table. Well, which one should we use? Well, we want to use the one that's closest to it. So the 0.1003 is 3/10,000ths away, and the 0.0985 is 15/10,000ths away. So clearly we want to use the 0.1001, and so we read off the z-score from the margin. So we look at that, and so the closest value is going to be negative 1.28. We don't worry about the negative. We kind of eliminate that. And so we always think of our critical z value as being positive. So the critical z star or critical z value for an 80% confidence interval will always be 1.28. All right, so how do we do this on our TI-84? So we use the inverse norm. That's going to be, you take your calculator and you look for the distribution. So the inverse, hang on, let me get my calculator. Make sure I'm saying the right thing here. So it's going to be the vars, the second function of the vars. It's the inverse vars, which is the distribution. If I get my calculator to work here. And then you go to your inverse, scroll down to find your inverse norm, and the area, that's the area to the left, in the left side, not the total, not 20%, but 10%, so 0.1, and it's a z, so we're on a standardized normal curve, so that has a mean of 0 and a standard deviation of 1, and notice that gives us our critical value the same as what we got on our z-score, okay? So so again, we ignore that negative we would get, and it's just 1.28. All right. So again, let's build up this formula a little bit more precisely. We had the statistic, which is the point estimate, which in our case is p hat, plus or minus the critical value. That's our z star that we've got. All right. So that asterisk is saying it's a superscript on the z. So it's not a multiplication dot or anything like that. It's p hat plus or minus your critical value or your z star, and then times the standard deviation of the statistic, really the standard error of the statistic, because we don't know p, so we have to put p hats in instead. All right, so the general formula here, critical z value, z star, is the critical value from the normal curve. We can either get that value from the z-score table, or we can do it with the inverse norm on our calculator. All right, so by the time we finish with this with this book, chapter 12, we will have under our belt about 13 different inference procedures. This will all make a little bit more sense when we start doing a couple more of them. But our first inference procedure, and remember, inference means we take information from a sample and say something intelligent about the population from that sample. So our first inference procedure is called a one sample z interval. Excuse me. And so it's a one sample. It's called one sample because we take one sample. And the distribution of our sampling distribution is a normal or z curve, and so we call it a z interval. Here we're creating an interval, confidence interval, and that's where the term interval comes from, and we're using it to estimate our population proportion. So this is a one sample z interval for the population proportion. So it's our first inference procedure. Okay, so suppose we take another sample from our container of beads. And in that sample, we got 13 red beads. We got 100 other beads that were not red. All right, so we want to calculate and interpret a 90% confidence interval for the proportion of red beads in the container. All right, now that last sentence we're going to talk about in a minute, but let's assume we don't know what P is. Now, your teacher's claiming that 25% of the beads are red. We'll talk about whether or not our sample data supports that, and our confidence interval, whether it supports that idea. So the first thing we want to do is calculate our sample proportion, or p hat. So that's 13 divided by 113. And so that's about 11.5% of our sample is red beads. All right, so we checked the conditions earlier, but let's review that. The conditions are that we randomly selected our beads using a simple random sample, that we're not violating the independence rule at a 10% condition. So we would have to make sure that we have more than 1,130 beads. And I think there's at least 1,200, something like that, beads in the container. So we're okay with that. And then the last one is that the large count condition holds, that that our expected number of successes and failures, expected number of red beads and the expected number of non-red beads in our sample this time. Normally we would look at n times p and n times 1 minus p, but here, of course, we have to do n times p hat and n times 1 minus p hat. And then those numbers are actually the 13 and the 100. It's the expected number of successes, or red beads, and non-red beads in our sample. So 13 and 100, both of those are over 10, so we're good. So we've checked our conditions again. Those 3 conditions we need to check every time. And we'll talk about how those are incorporated into your 4-step process too. All right, so we want to find our critical Z value. So I went through this is one little section of our Z-score table. So if you want to go and look at your Z-score table, try to find, let's think about this. We have 90% inside the confidence interval, right? So that means we need 10% outside, total outside, and then in each tail, it's going to be 5%. So we're looking for, on a Z-score table, we're looking for 0.05. And you can see there are 2 numbers there, and they're both equally distant from 0.05. And so we would simply, in that case, take the average. The 2 numbers would be negative 1.64 and negative 1.65. So we take the average of those, or 1.645. So that is our critical value. Remember, we only think of it as positive. So their Z star will be 1.645. All right, so now what we want to do is calculate our confidence interval. So your p hat plus or minus critical Z star times the standard error of the statistic. All right, so kind of a complicated calculation. What I would expect is that you would kind of get to this step. You want to sort of write that down. It's your point estimate plus or minus your margin of error. So the margin of error in this case is 0.0494, but you don't want to leave your answer like that. You want to leave it as a interval, so the low end and the high end of the interval. So you want to take 0.1150 and subtract 0.0494, and then you want to take, that gives us the lower value of 0.0656, and then you want to take 0.1150 and add 0.0494, and that gives us the higher value on the interval of 0.1644. All right, so you don't want to leave it as a plus or minus. You want to actually give us the low and the high bound on the confidence interval. All right, and so then we'll want to sort of interpret that. So this is how we interpret it. Remember, we have 3 components to it. We are, and we say how confident we are, what the confidence level is. So we are 95% confident that, and then we say the interval from 0.0656 to 0.1644, and then captures what? The true proportion of red beads in the container. So 3 components to a proper interpretation of the confidence interval. We are 95% confident. We give the interval, and then in context that interval captures what? True proportion of red beads in the container. Now, all right, let's go back to the question up above, the statement up above that says your teacher claims Your teacher claims that 25% of the beads are red. So does our result support that? And so you can kind of see if we look at our result that we got a confidence interval between about 6.5% and 16.5%, something like that, right? So somewhere between, if we round it to whole numbers, 7 to 16%. Well, 25 is not in that interval. So that would mean that our confidence interval does not support your teacher's claim that 25% of the beads are red. So since the interval gives a range of plausible values, that's what a confidence interval does, gives us a range of plausible values for the parameter, in this case P. And since the 25% is not contained in the interval, it just does not support that claim, right? So we have reason to doubt your teacher's claim that 25% of the beads are red. All right, so let's look at your four-step process. Again, it's been a while since we've done 4 steps. Remember that this symbol in your book indicates that a problem should be done in 4 steps. They will show that for a while, but eventually at some point they'll stop showing that, and you will be expected to know when a problem should be using 4 steps. And we'll talk about that as well. So we'll give you some indications. To start with, we'll tell you when 4 steps are required in most of the problems. All right, so the state. The state is you're basically saying what it is you're trying to estimate. So for confidence interval, we're going to say, well, we're going to use a confidence interval to estimate the true parameter, or in this case, the true population proportion, because that's what we're dealing with in this section. All right, then in the plan, we identify the inference method. So that's the inference method that I was just talking about. The one sample Z interval for P is the only inference method or inference procedure that we know so far. And then we also need to check, after that, we'll have to check our conditions. So our 3 conditions get checked at that point. The do is we perform the calculations. So we calculate the confidence interval in this case. And then the conclusion at the end, use it, you're interpreting your confidence interval using your sort of 3 components, right? We are such and such confident that the interval from blah to blah, and then captures, and then what it is we're trying to estimate. All right, let's go through an example. All right, so a random sample of students who took the SAT twice found that 427 of the respondents from our sample had paid for coaching courses, between the 2 takings of the test, and the remaining 2,733 of the respondents said that they did not engage in any kind of coaching. Or by coaching, we mean, that you took a class or you hired someone as a tutor or something like that. All right. So people took the SAT, and then the second time taking it, did you receive any kind of coaching or tutoring or anything, before taking it the second time? All right. So we want to construct and interpret a 98% confidence interval. So those are words that tell you, 4 steps are required. So constructing and interpreting a 98% confidence interval are the clues that you will get used to seeing and saying, I got to do 4 steps. All right. So they obviously are telling us at the top right corner here that we should be using 4 steps, but that construct and interpret a 98% confidence interval tells us that 4 steps are appropriate here. All right, so we're trying to do a confidence interval for the proportion of coaching among students who retake the SAT. So we have a sample, and in that sample, 427 students that we sampled said that they did receive coaching. 2,733 said they did not. So that gives us a sample proportion. We want to use that to try to estimate the true proportion of all students who take the SAT twice. What proportion of those students, of all students who take the SAT twice, receive coaching? All right, so step 1, or what we're going to call the state. All right, so the state. we want to estimate. What is it that we're trying to do? We're trying to estimate the proportion, P, of the population of SAT retakers who are coached. All right. And we want to use a 95% confidence level. So we're telling three things there. What are we doing? Right? What are we trying to estimate? And also we want to say with what confidence level. All right. All right. The next part is the plan. So in the plan, we will state the inference procedure. So first thing, we're going to use a one sample Z interval for P. We're using P hat to estimate that P. And the conditions, we took an SRS. We are going to assume that our sample is less than 10% of the population of retakers. And we need to check our large count condition. So again, not N times P, but N times P hat and N times 1 minus P hat. Well, that's in our sample, that is the people who said yes, they did coaching, and people who said no. So it's the expected number of failures and the number of failures and the number of successes in our sample, because we don't know the population parameter. Okay, and so both those values are greater than 10. That's our large count condition. All right, so now we can go on to our do. First thing we want to do is calculate our P hat, our point estimate. And then we need to calculate our critical Z value. So our critical Z value, remember we're doing a 98% confidence interval. So that's 98%, that's inside under the curve. So how much is in the tail? That's 2%. And then how much is in each tail? 1%. So we are looking for 0.01. And notice we're on the negative Z-score table. We're looking for 0.01. So if we look, that's the closest there. And so we read off our Z-score, and our Z-score would be negative 2.33. But of course, we always just think of it as positive when we're thinking about a critical Z value or Z star. So our Z star is 2.33. So that is our critical value. So you can see we put that in, we can see that is right here in our calculation. And then we have our P hat, 1 minus P hat over N. And so again, don't leave your answer in this format, right? That's what you're going to find first. It's the point estimate and then the margin of error. But actually subtract those two and then add them to get our actual confidence interval. All right, and then the last part, the conclusion, you're interpreting that. So 3 different components there. Remember, we are 98% confident that the interval from, if you want to say 12% to about 15%, but 4 decimal places is also good. So those in that the 98% confident that the interval from 0.1209 to 0.1493 captures, and then say what it is we were trying to estimate, the actual proportion of student retakers who got coached. All right, so we have some homework from this section, and the last two, 35 and 36, are 4-steppers. So make sure that you're using that and getting used to now 4 steps. So instead of saying step 1, step 2, step 3, step 4, use the term state, plan, do, and conclude when you're doing those. All right, and so that homework is due next class.